Hi, my name is Chris Beauchamp and I'm a mobile developer with Kii Cloud, and this is the third part in a video series on building an iOS game using SpriteKit and Kii Cloud. If you missed the first two parts of the video series, I definitely suggest going back and checking those out. You can find those in the links down below the video. You definitely want to do that, especially if you're new to SpriteKit. And in the first two parts of the video series, we went over how to create a SpriteKit project, then how to interact with the physics world and create a few physics bodies within our game. And in the second part, we moved on to actually create the game board for our game. So to get started here, we'll show you where we left off by doing a quick build and run. And we just have a few, that's 6 columns and 7 rows of blocks just falling down onto the floor. Now if we see what's happening in the code, you'll see that here we're iterating through a couple of for loops to create a block down here for each row and each column within that row. Now what we're going to do is take this create block method and kind of refactor it a little bit. So we want to make these blocks their own class because we want some custom attributes associated with these blocks so we can start tracking them and start performing some more advanced functions on them. So we'll go ahead and do that now by creating a new class. And we'll call it block node. And this is going to be a subclass of SK sprite node. We'll save it in our project. Reorganize a bit. Now we want to add a couple of properties to this class as well. So we'll go ahead and do that. And these properties will keep track of the row and the column that the block resides in. Simple enough. And we also want to create our own initialization method. We'll clean this up a little bit. And then go over and work on the implementation. And now it's time to actually get into the good stuff. So we'll set our assignments, so the properties that we defined earlier. We'll set that to the parameters that were passed in. And then we want to add things like the physics body and actually set the parameters of the node. So we've already done that in our scene file, so we'll go ahead and copy and paste that out. So this bit of code right here will still be useful to us. And we'll just paste it right in and modify it to act on itself rather than on a block variable. And here you notice we have the position. In the scene file, we're taking that from a parameter. But we'll actually go back and we'll use this right here, which is based on the row and the column. And we'll just use that to create our position within the initialization method. And here we're also going to change our row and our column to the variables that we have in our class. And this should be good for our initialization method. So notice we haven't really done anything different. We're just kind of reorganizing things into this block node class. So we'll go back into our scene and we'll import the block node so we can actually use it within this implementation file. And of course we need to modify how the blocks are created. So we'll go into our create block area and use the class rather than use the method. We'll get rid of the existing method call and add this to our scene. And we can go up here and get rid of this method because we're not using it anymore. So now we've just reorganized and kind of refactored the code to use this block node class. Now we should be able to build and run and have the same result as what we saw earlier. And we do. So all of our rows and columns are still being created with random colors. Now the next thing we want to do within our gameplay is allow the user to be able to click on these boxes to get rid of them. Right? So it's the first step that we're going to take toward actual gameplay. So we'll go back into our scene and start to handle the touches. And you can see Apple, in their template, they already had some code here to handle touches. And we're going to create our own. And the first thing we're going to do is just grab one of the touches that is happening on the screen and get its location. So figure out where on the screen the user is touching. And based on the location of the touch, we can figure out which node that they're touching, if any. So we'll say SK_sprite node. And we'll just print out a log for now to see which node was clicked. Now if we build and run, we should be able to start clicking on nodes and seeing some output here in the log. And we do. So you see we clicked on this SK_sprite node here with a given position and size. And we can keep doing this for any of these nodes. But notice we can also click on the floor and we're getting output for the floor as well. We don't want to capture that. So we can go in and we can actually filter which node is being touched in our touches began method. So we'll use a little bit of filtering here and just call this a node, skNode. And use the same method here. Now we're going to test to see if this node is a block node or not. And if it is, then we're going to register the click. But if not, we're not going to bother with anything. So this should filter our touch method to only react when you click a block node. So you can see when we click a block, it's still registering. But if we click the floor, nothing happens. So this is exactly where we want to be. Now we want to figure out which block that we're clicking on. So we want to get the row and column of the block that's being clicked. So we'll cast it as a block node so we can access these attributes. Oops. And this is safe to do since we already are sure that it's of type block node, so we can go ahead and cast it safely. And we'll get the row and column here. Now if we build and run, we should be able to see the position of the block node that's being touched. So this one here is row 6 and column 0. So it's row 0, 1, 2, 3, 4, 5, 6, and column 0. Remember, it's all zero-based arithmetic here. And if we click on this guy at the top, it's going to be row 0 and column 5. And anywhere we click, we can get the index of the block that's being clicked. And the reason we want to do this is to figure out if any of the blocks around it are the same color. And if so, we're going to remove those blocks from the screen. And to do that, we're going to iterate through every node, every block that's on the screen, and see if that block is within range or touching the block that was clicked. So let's say we click this block here. We want to get the 4 blocks around it, on the top, on the bottom, on the left, and on the right, and see if any of those blocks are the same color. So we'll implement a little bit of iteration logic here. Actually, before we go too much farther, let's create an easy method to access all of the block nodes that are on the screen, so we don't have to keep doing this kind of filtering and then casting. So we'll just make one easy to use method, and we'll use the same kind of logic, but we'll just be able to reuse this whenever we need it, because it might come up here down the road. So all we're doing here is iterating through every node in the scene, and we should actually call this skNode because we're not sure the type, and checking if that node is of type block node. And if it is, we'll add it to this array and return all the blocks at the end. So now we can just use an easy for loop. So now we have all the block nodes and we can iterate through them much more easily than kind of copying, pasting all of this logic here every time we need to get all the blocks. So the next thing we want to do is figure out if this child node is within range of the node that was clicked. So we want this method to look something like this. So this method hasn't been created yet. We're just kind of thinking, what do we want to test? We want to test if the child node is in range of this block. And we'll actually name this click block to make things a little easier to read. Make a few changes here. And now we just need to go about creating this method. We'll make it a Boolean. Now if you look at our game board, we want to know if the block is in the same column, and if it is, if the row is within one of the click block. So that's just getting above and below. Similarly, if the block that's being tested is in the same row, we want to make sure it's within one column of the block being clicked. And if either of those cases are true, then we know we have a block that's a neighbor to our click block. So we'll implement some logic, and we'll spell it out really nicely here just so it's a little more easy to read. So we'll test to see if it's in the same row and also in the same column. And then also test to see if it's a one-off. So if we click on this block, if it's one off to the left or one off to the right, similarly top or bottom. So we'll implement a couple Boolean values for that as well. Actually, we need to switch that. Make our base node. And we'll do the same thing with rows. And finally, we're going to return if it's in the same row and it's only one off column. So logic looks something like this. Or if it's in the same column and it's only one off of the row. And if either of those are true, that means that the block is within range. So now we only want to show children if they're in this range. So we'll test for it there and then print a log if it is. Now if we build and run. Now if we click on this node here, we should get a log for the node being clicked. And then we should get two children around it, the one at the top and the one on the right. So let's see, hopefully that happens here. So again, we got the node clicked and we got the two children within range. So the one on the right and the one on the top. But now we also want to filter for color. So we only care if the block is in range if it's the same color. Because remember, we want only the colors that are matching to disappear from the board when the user taps them. So we need to modify our inRange method here and also test for color. And we need to wrap our return statement because this still needs to be true. And also it needs to be the same color. So now if we build and run again, let's find one of these blocks that we can use. So if we use this one on the bottom right, we should only get one child within range, and it should be the child right above it. And that looks to be the case. So if you look in the log here, the node that was clicked was at position 292 and 65, so that's this guy here. And the child in range is at x292 and y position 116, so it's right above it there. So it looks like this is all working as planned. Now the next thing we want to do is actually remove these blocks from the screen. If we click on a block that has a matching partner next to it. So what we'll do is create a tracking array here of objects that we want to delete. And we'll initialize it with our click block object. And if the child is in range and it's valid, i.e. it's the same color, then we'll add that to the objects to remove as well. And once we've compiled all these together, we'll iterate through and delete them. And to do that, we'll just remove them from the super view. Now if we build and run, when we click a block that's next to a friend, they should both delete, and they do. And notice that the physics engine takes over and the blocks that are sitting on top of it will fall right into place. But also note, if we click on this yellow one here, the game defines that all of the connecting blocks should be removed. But so far in our logic, we're only looking at the blocks immediately above, below, to the left, and to the right. So if we click this yellow block here, only the one to the right will delete. This whole line of blocks here will not, as shown there. So we need to make a bit of recursion in here to make sure that we get all of the blocks that are touching the block that was clicked. And we'll do that by creating a new method over here. This method is going to use recursion to walk through every valid block that's next to our click block, and then walk through every block that's around that one. So it's recursively going to iterate through every valid block to look for neighbors around it that are also valid. So to do that, we'll use this. And through the method definition, you can see that we're just looking for the nodes that we want to remove that are around or touching the main node. So we'll do that by kind of reusing the logic that's down here. And first things we want, let's actually rename this as the base node. And first thing we want to do is add that base node to our array. So we want to make sure that the base node is actually being deleted. We need to update our naming here, so this is the base node. And when there's a match, so when we have found a child that's in range, we want to make sure that we haven't already matched it. So we'll do a simple array test here. So if the child node that we're testing is not already in the remove nodes, this is when we're going to add the recursion. So we're going to test that node to see if any of its neighbors are also the same color. And we're going to look around the node, this child node. Finally, we're going to just go ahead and return the entire array at the end. And hopefully this bit of recursion here will work as expected. And down here, we want to define the objects to remove as this recursive method. So we'll go ahead and do that now. And we'll start with a blank array and searching around the node of the clicked block. We'll reorganize a little bit. And we're still going to remove these from the parent. So we'll build and run and see if this recursion helps. So here we've got a block that's 4 blocks wide. So if we click this, hopefully all 4 blocks will disappear. And they do. So our code is successfully walking through all the neighbors to look for valid blocks around it. But also note that if we click this single blue block down here, it'll also disappear. And that's because we haven't set up any logic to ensure that 2 or more blocks have to be connected before they disappear. So we'll jump back into the code and make sure that has to be the case before these blocks disappear. And we'll actually set that as a constant up here. We'll call that minimum block bust. And for now we'll say 2, and you can change this later if you wish. So before we delete anything, we want to make sure that the number of objects we're removing that are valid is greater than that constant we just defined. And greater than or equal to, because we want 2 or more. And if that's the case, then we go through and remove all the objects. So now if we go back in, you can see if we click this single one here, nothing should happen. But if we click this trio, they should all disappear. And they do, so we're looking pretty good. So now if we keep clicking and playing around with our game, something weird happened. So watch this big chunk of blue blocks. So we click this one down at the bottom and we expect them all to disappear. But that's not the case. Only about half of them disappeared. And the reasoning behind that is because our row and column of our blocks is not being updated. So when blocks disappear below, the blocks above, their variables don't change, their parameters don't change. So the row and column, even though it fell and is a lower row, the program is still looking for this block at the very top level, and it still expects it to be there. So what we need to do is walk through all the nodes, all of the blocks above what is disappearing, And from there, just decrement the row every time a block underneath it disappears. And if it sounds confusing, hopefully the code will make much more sense. So whenever we remove an object, we want to get all of the blocks above it and then decrement the row. And that looks something like this. And this bit of logic here is checking to see if the two nodes are in the same column. And if they are, if the one that's being deleted is in a lower row than the one that we're testing. So we'll rename this just to make it a little more clear. So if the test node is above the node that we're deleting in the same column, we're going to go ahead and decrement that. So we'll set testNode.row to 1 below what it is currently. So we'll go ahead and see if this helps. So to test this, we'll get rid of these green blocks here and watch these yellow blocks fall down. Now these yellow blocks that just fell, hopefully their rows are changed and they'll be affected when we click this block down here. And they are, so it did update and it's working as expected. Now we're noticing that we need new blocks to fall into place. So whenever blocks disappear, we want new ones to fall from the top, so we always have a full game board. And we'll do that once any objects are deleted. So we'll insert a bit of logic here at the end of the block. What we're doing here is just creating an empty integer array, and we're going to count how many rows are in each column. So we're going to iterate through every block in the screen and get its column and row. So this logic right here is just finding the maximum row in each column. So it's checking to see if the row that we're testing currently is greater than the previously found maximum. And if it is, then we're setting that to the new one. So this is just getting the top row in each column. So in this case, it'll be 0, 1, 2, 3. And in this case, it'll be 1. And it'll do that for each column across the board. So once we have the total number of rows in each column, we want to make sure they're all filled up. And to show this, we'll just do a quick log, just to illustrate what I'm talking about. So if we click these blocks, they disappear and the rows are updated. So here in column 1, there should be up to 5 index rows. So 0, 1, 2, 3, 4, 5. In the next one, it's up to 2, 0, 1, 2, and then up to 4, and the rest are all filled at 6. So this is working as we expect. And it's just getting, again, it's getting the maximum index for each column. The maximum row index for each column. So as long as the column doesn't have the maximum number of rows, we need to start filling it up with blocks. And we can do that with something like this. So we're just iterating through and making sure that every row is filled up. And right here we want to put our block creation. And since we don't want to reinvent the wheel, we can just go up and snag what we built before. And get our dimension and our colors and our color index and our block node. And since we're not tracking the row, we can just figure out which row this is going to end up in. And we want to make sure at the end of our while loop we're incrementing this total rows count. Now one last thing while we're here, we're going to make these colors an IVAR, so we don't have to keep defining them and tracking them across multiple points. So what I mean by an IVAR is we'll define it up here, and now it can be accessed throughout the entire class. So we'll update it, rather we'll create it in our initialization method. we'll pop it up here at the top so it's easy to find. And we'll make sure this is referencing that iVar as well. All right, so now let's go ahead and build, and hopefully we get a build failure. Oops, didn't update my iVar all the way across. Sloppy programming. So hopefully when we click this block here, all these will disappear and we'll get some new blocks filling in the place. But the expected result isn't exactly what happened here. So what's going on? Well, it looks like when we click these blocks, the rows are actually popping up below. So see, they're kind of filling in from the bottom, where we want them to fill in from the top. So if we go back into our code, we see that the row is being created correctly, and so is the column. So let's dig into our initialization method to see where the block is positioned when it comes into the screen. And we specifically want to look at this Y position. So right now, the larger the row, the lower on the screen the block will appear. So that's why when we're popping blocks on the very top of the column in the highest row, it's coming in at a very low Y on the screen. So it's coming up from the bottom. So if we just switch this to a plus, we should be able to invert that and have the higher rows falling in from higher up on the screen. So let's see if that does the trick. Now hopefully when we click this big mess of blocks, we'll get some falling down from the top. And here they come. Looking pretty good. So now we're seeing these new blocks fall in, but it's all moving a little bit slow, so let's make a few tweaks. So we're going to go back into our main scene and alter the physics of the entire world. So right now, the gravity is at -1, and we're going to change that to -8. So these blocks really come flying down fast. So as we start clicking, you'll see the blocks come down much faster. And this is ideal for the fast-paced gameplay that we're looking for, so we'll go ahead and leave that as is. A few more tweaks that we can try to make is, let's change the number of columns to 4 and the number of rows to 5, and the minimum blocks that need to be connected to 3. So we just changed a lot of definitions here. And you'll notice that the columns are much wider, so they might be easier to tap. But the minimum blocks that you need connected are 3, so this one here won't work, but this one will. So just changing these minor definitions can change the entire gameplay within your app. But we'll go back and leave that as is, as was before rather, and change one more thing before we're done. And we're just going to add a new color. And we'll add purple. So just by changing the colors, iVar, the game gets a lot more tricky because there are more colors on the screen and not as many blocks are connected. So you can add as many colors as you want, you can take away as many colors as you want to change the gameplay however you wish. And it's actually starting to be pretty fun. So that's where we're going to leave things today. And we'll have a couple more parts to this video series in the immediate future to really round out this game and give it scoring and even a high score backend in the cloud. So definitely take a look at those videos coming up. And in the meantime, as I've said all along, this project is open sourced. And if you want the code specifically for this tutorial, go into the tag tutorial 3 in our GitHub project page, and you can get that using the links shown here. So we hope you enjoyed this lesson, and hopefully we'll see you back for the next one, where we'll actually start to add a scoreboard and make this into a full, complete game. Thanks for joining us.